All right, ladies and gentlemen, today's class recording has started. So, in the last unit, we introduced some terms that describe different aspects of different atoms for us. For instance, we talked about the atomic number. What does the atomic number of an atom tell you? How many protons it has, and electrons. Although we'll learn in a couple of units that number is not always the same. It is now, but it won't always be. Okay? Then we introduce the concept of mass number. What does the mass number tell us about an atom? What's good? Number of protons plus the number of neutrons. So here we've just been identifying the different number of pieces or subatomic particles that make up a specific atom. But we really haven't compared atoms to one another. That's what we're going to be doing here in the first part of this unit, comparing atoms to each other using something that we call the average atomic mass. And so by the end of today, we'll hopefully define what average atomic mass is and talk about where it comes from and how to calculate it. And that discussion starts with something that we call isotopes. What is our definition of isotopes? Andy, you want to take it? Good. Atoms that have the same number of protons but a different number of neutrons. With that being said, what will be true about the atomic number of these atoms? They'll be the same atomic number, but what will be different? The mass number will be different, okay? So, if you're filling in your outline, Roman numeral 1, letter B, they're the same element, but they have a different mass, all right? And then for Roman numeral 1, part B, number 1, we can say that they have the same atomic number, but they have a different mass number. All right. Good so far. On the periodic table, when you look at the little key up at the top, right, it says that there are 4 things that are in every square on the periodic table, right? It's got the element name, that's pretty obvious. It's got the atomic number, which is the integer number that is the second thing down in each square. It's got the symbol for that element. But then the bottom number, if you look up at the little key up at the top, the bottom number in each square says it is the atomic weight, which we sometimes call the average atomic mass. Okay? That is none of the things that we have talked about before. We have talked about mass number, but we have not talked about atomic mass. So that is where we go today. Mass number versus atomic mass. Like we said, mass number tells us the number of protons plus the number of neutrons. The mass number is always going to be an integer value. It will always be a whole number because we are basically counting. You're counting the number of protons plus the number of neutrons. If you look at the periodic table, you will see the only integer value that shows up on the periodic table is the atomic number. Mass number does not show up on the periodic table. That number on the periodic table is called the average atomic mass. So let's describe that in a little bit more detail. Atomic mass is a relative scale. Right? This doesn't go exactly in the order of your outline, so let's talk first and then you can fill in the outline. Okay? Atomic mass is a relative scale. What does that mean? We describe something as a relative scale. What does that mean? It's comparing things. Now, if we are going to set up a relative scale to compare things, what has to be the first step in that process? Okay, I'll give you. That's the important part, right? Having more than one thing, true, if we're going to compare things, we would technically have to have more than one thing. But the more important part is having something to compare it to. If we're describing or comparing different things, what are we comparing them to? And so atomic mass is a comparison that compares the size of an atom to one particular atom, that atom being carbon-12. Carbon-12 is the basis for the comparison is our basis of comparison for all the other atoms. If you know an atom is called carbon-12, you should be able to tell me 3 things about that atom. Someone besides you? What 3 things can you tell me about that atom? It has 6 protons, and we know that why. Atomic number of what? Carbon. The atomic number of carbon is 6, so it has 6 protons. What else? Well, do you want to keep going? It has 6 neutrons. This number 12 that comes after the name, that's the mass number, right? Mass number is protons plus neutrons. If 6 of those 12 are protons, the other 6 have to be neutrons. What else do you know about that atom? 6 protons, 6 neutrons, 6 electrons, because they're all basically, the protons and the electrons have to be the same, okay? So, that atom is the basis that we compare all of the other atoms to, okay? Now, with that being said, we have set up a scale that we call atomic mass units. That name is a little misleading. Atomic mass units are not a measurement. They are a comparison value. And again, well, what are we comparing it to? We give carbon-12 a value exactly equal to 12. So we say that carbon-12 gets a value equal to 12.0000000000000000. Keep going. It's exactly 12. And all the other atoms get a value based on that. If some hypothetical atom had an atomic mass equal to 120, what would that tell you about that atom? If the atomic mass of some hypothetical atom was 120, what would it tell you about that atom? It's 10 times bigger than carbon-12. Follow me? Okay. If some hypothetical atom had an atomic mass of 60, what would that tell you about that atom? It's 5 times bigger than carbon-12. If some hypothetical atom had an atomic mass of 4, what would that tell you about that atom? It's 1/3 as big as carbon-12, right? That's the comparison system that we've set up, these atomic mass units. They compare an atom to carbon-12. Okay? Good for starters? All right. Carbon-12 has a value of 12.0000000000. Look on your periodic table. Find carbon. What is the mass number that is listed there? 12.011. Is that what it says? 12.011. Is that exactly 12? No, it's close, but it's not exactly 12. So that number must mean something different, right? So what does that number mean? The discussion of what that number means starts with these two charts. You have these two charts in your outline. First thing I need you to do, these two columns over on the right-hand side, nuclear spin, magnetic moment, cross them out. We're not going to, way beyond the scope of what we're doing here, okay? It was part of where I grabbed the from. You do not need to know that at all, okay? But we are going to focus on the first three columns. Isotope, atomic mass, natural abundance. Those three columns. Okay? All right. First isotope, carbon-12, right? The C represents carbon, the 12 represents its mass number, right? Will, you already told us, what do we know about carbon-12? 6 protons, 6 electrons, 6 neutrons. And you see here under the column that's labeled atomic mass, what is the atomic mass listed here? 12.000000, right? Okay. Next one down, C13, carbon-13. What can you tell me about a carbon-13 atom? How many protons does it have to have? 6. It's got to have 6 protons still because it's still carbon. But if its mass number went up from 12 to 13, what has to be true about it? It's got 7 neutrons. These two atoms, carbon-12 and carbon-13, what word would we use to describe them? Those are isotopes of each other. They are atoms that have the same number of protons, but a different number of neutrons. Good? Okay. Atomic mass. Look at the atomic mass listed for carbon-13. 13.003354. What does that number suggest to you? What conclusion can we draw from the fact that the atomic mass of carbon-12 is exactly 12, but the atomic mass of carbon-13 is 13.003? What conclusion can we draw from that information? Anybody want to give it a shot? Go ahead. Good. Carbon-13 has more neutrons than carbon-12. What does the fact that the mass went up by a little more than 1 suggest to you? Okay, increases by a non-constant rate, that's true. What changed about the atom itself? What changed about the atom itself? Okay, go ahead. 1 neutron was added, but the number went up by more than 1, right? A little bit more than 1, but by more than 1. What does that suggest to you? It suggests that neutrons are a little bit bigger than protons. Does that make sense? Right? That the fact that we added 1 neutron and the value went up by a little bit more than 1 suggests that maybe protons are a little bit bigger than neutrons. Good? Okay with that? All right. Next, let's go down to the second table. Okay? The first atom that is listed in the second table is listed as 24 Mg. The fact that it's Mg tells you it's what kind of atom? It is magnesium. Okay? The fact that it is a magnesium atom should tell you what about it? It has 12 protons and 12 electrons. The fact that its mass number is 24, how many neutrons should that atom have? Still 12, right? So 12 protons, 12 electrons, 12 neutrons. The next one down is magnesium 25. How many protons does magnesium 25 have?
12.
Still 12. But how many neutrons will it have? 13. Magnesium 26 still has how many protons?
12.
12. But now how many neutrons? 14. What's true about these three atoms? They are isotopes of each other. They have the same number of protons, but a different number of neutrons. These are three isotopes of each other. The two up on the top are isotopes of each other. Okay? Good with that. All right. Now, here's something to make it a little bit more confusing. Hopefully not, but okay. So we talked about that going from, on the top, exactly 12 to a little bit more than 13 suggests that neutrons are a little bit bigger than protons. Good? Here, magnesium 24, 12 protons, 12 neutrons, 12 electrons. How does that compare to the number of protons, neutrons, and electrons in carbon 12? It's exactly double. But what are you seeing about the atomic mass? It's not exactly double. It's a little bit less. What does that information suggest about protons, neutrons, and electrons? They're not all the same. If they were all the same, doubling the number of them would exactly double the atomic mass. But if that doesn't happen, okay? All right, good with that for starters.
Yes.
Okay, here, atomic mass of these three magnesium isotopes, 23.98, 24.98, 25.98. That sort of fits the pattern, right? We're adding a neutron, we keep getting a little bit bigger, basically by 1, okay? However, take a look at your periodic table. Find magnesium on your periodic table. What is the atomic mass listed on the periodic table? 24.305. That's not any of these values. Right? So, if we have three possible atomic masses, what should we probably do with those values? Average them. But if you average these three numbers, right, you should get something that's pretty much the middle. Is the number on the periodic table the middle of these three? It's not, right? That's where the next column comes in, this natural abundance, right? This is a percentage. Here's what we find out there in the real world. If we took a sample of 100 magnesium atoms, random 100 magnesium atoms, we could never just get 100 magnesium atoms. They're way too small for that. But if we could, what we would find is that of that 100, 79 of them would have 12 protons and 12 neutrons. 10 of them would have 12 protons and 13 neutrons, and 11 of them would have 12 protons and 14 neutrons. They're all magnesium, but they're a little different. This is how they are distributed out there in nature. Each sample of magnesium that we obtain, 79% of the atoms are 12 protons and 12 neutrons. 10% of them are 12 protons and 13 neutrons. 11% of them are 12 protons and 14 neutrons. That's how we find them. Okay? So, on the periodic table, the atomic mass of magnesium is listed as 24.3. Which one of these is the closest to 24.3? 23.98 is the one that's closest to 24.3. Is that a coincidence? No. We're averaging three numbers, but do those three numbers contribute evenly to the average? More of them are magnesium 24 than any of the other ones. Does that make sense? Okay? So, where does that number come from? That number on the periodic table is what we call the average atomic mass. What did we say that atomic mass does? That's mass number. Okay? Atomic mass, it's up earlier on your outline. What does the atomic mass do? Go ahead. It tells the size of an atom relative to carbon-12. Average atomic mass is something a little different. Not all of our isotopes occur in the same proportions. We just saw that. Average atomic mass takes into account the size of those isotopes, their individual atomic masses, but also what percentage are we talking about? So not only the individual atomic mass, but how many of those atoms are there? Okay? So we take into account the individual atomic mass, but also then the distribution. What percentage of those different isotopes are there? All right, good? Last second, almost done. To illustrate that point, let's take a look at the pictures that are at the top of the page on the back side. Okay? I'm only going to look at one half of it at a time. If you're watching the video, you can't see this, but for you guys in class, you can. Okay. On the left of that picture is a sample of bromine. And it didn't copy very well, but here it is up on the board. Okay. Question number 1. How many isotopes of bromine are there? How many isotopes of bromine are there? Talk to the person next to you. Come up with an answer. 8. Alright, so how many isotopes of bromine are there? 2. There are 2 isotopes of bromine, right? Now, there are 2 isotopes of bromine, right? Bromine 79 and bromine 81. Okay? You should be able to figure out how many protons and neutrons they have, but let's not worry about that right now. Okay. In this flask of bromine, bromine is a liquid at room temperature, okay? That's why it's blue up on my periodic table on the wall over there. And there's not many that are blue. Bromine is one of them, okay? All right. Here is a random sample of 8 bromine atoms. There is no way that we could ever isolate 8 bromine atoms. But for our purposes, let's say we could, okay? What are you noticing about the distribution of isotopes of bromine in that 8-atom sample? Pretty even, right? We got 4 79s, and we got 4 81s. If you took an average of those 8, right, the average comes out to be 80. Are there any atoms that are actually bromine 80? No, none of them are. But the average is 80. You got half 81 and half 79. We can't separate the 79s from the 81s. They're all mixed together. So when we're talking about a sample of bromine, we use 80 as the mass of that bromine because half of them are 79, half of them are 81. The average is in the middle. Okay? Good with that. Here's chlorine. Chlorine is a gas at room temperature. That's why it has this container with this little spigot on the side. You can attach a hose to it and stuff like that. All right? Question number 1. How many isotopes of chlorine are there? 2. There are 2 isotopes of chlorine. What are they?
35 and 37.
Chlorine 35 and chlorine 37. Okay? Again, you should be able to figure out how many protons and neutrons those have, but we don't have to do that right now. Okay? All right. But if we look at a random 8-atom sample, what are you seeing about the distribution? There's more 35s than 37s, specifically about 75% 35, but only 25% 37. If you take the average of those 8, right, you won't get an even number. You'll get 35.5. When there is an even distribution of isotopes, where is the average in regards to the 2 isotopes? Where does the average fall? Right in between the 2 of them. Does that make sense? But here, which one is the average closer to? 35, because there's more of them. Well, I mean, let's say we were going to the 10th place, right? In this case here, the average is closer to 35 because we have more 35s. Therefore, the average is going to be closer to that number because there's more of them. Does that make sense? Right? Same thing. If we're mixing paint together, right? If you mix equal numbers of blue and yellow, what are you going to get? You're going to get a green paint. But if you add twice as much yellow as you do blue, is it still green? Yeah, but it's going to be what? It's going to be more of a yellowy green, right? If you have twice as much blue as you do yellow, it's more of a tealy color, right? It's more blue than yellow, right? Same thing here. We have these numbers. The one that's closer to, or the one that there's more of is closer to the average. Okay? Good for starters? Okay. So, to wrap this up for today, how do we take into account the, oh, I need to zoom that out so you guys can actually read this. How do we take into account the different isotopes? These 8, hold on, we're almost done. We're not done yet. All right. How do we take this into account? Here is an equation that shows how we take this into account. First, atomic mass. What did we say the atomic mass does for us? Relative to carbon 12. Okay? But then we multiply this by a fraction. Abundance is how much there is of it. This is a percentage. Okay? If you put a percentage over 100, you basically turn it into a what? You basically turn it into a decimal, right? Okay? But we do this for all of the isotopes. So for chlorine, how many times would we have to do this equation? How many isotopes of chlorine are there?
12 times.
2.
There are 2 isotopes of chlorine, right? Down at the bottom of your page, right, you have isotopes of zinc. How many isotopes are there down at the bottom? There are 5. You would have to do this calculation 5 times. At the end of the day, the sum is the average atomic mass. Once you do this calculation 5 times for zinc, what do you do with the answer to those 5 calculations?
Average.
No.
What?
What does it say by the bullet point? You add them together. The sum of these calculations turns out to be the average atomic mass. Okay? All right. Tonight, there are a couple of pages and a couple of examples from your book that are listed on your calendar. Make sure you take a look at those. Tomorrow in class, we will do an example of this calculation, and then we will start looking at some other calculations that we call conversion factors. Take a look at the listing on your homework, on the calendar. There it is right there. Okay. All right, we'll see you tomorrow.